Okay, we were talking about this. The vanilla RNN plus a output layer, the matrix multiplications. I mean, when you understand this, it's quite a simple thing actually. So at this point, I'm going to switch to another figurization of it, a simpler depiction. But I'm going to keep the same formula. So what I'm going to show you will not change. I mean, it will be the same thing internally, but I'm going to change how it looks. So instead of this, I'm going to get this core RNN, rotate it. But for all nodes, you see, when I rotate this, there's a node, this node becomes this node becomes, and so I rotate it in a counterclockwise direction by 90 degrees. And instead of using many nodes, I'm going to use a super node representation. So this is it. I mean, the vertical vector will be a horizontal vector fed to the number of k nodes. This is a super node representation. It will provide me k nodes, and it's recurrence. So that's why the formulation you had here will apply. Okay, so whatever you see this sign, it's going to be this recurrent connection because it's got its recurrent connection as well. So I hope it won't confuse you. Okay, I mean, it's quite simple. It will be the same depiction actually, but in a more, how can I put it, simpler way. There's a reason we do that. So when you look at it, it is the input, it is the previous hidden state, the next hidden state. So instead of saying previous or next, I've designated time indices like a time series, data type. So it is ATI, a time instant, and this is the next time instant. I'm thinking that they are discrete steps of time. And it still holds. So instead of A previous, I say ATI. Instead of A next, I say ATI plus 1. Nothing changes. And inside, we have this K by K plus N matrix plus the K biases, because this supernode includes K nodes. I hope you don't have a problem with that. So what I'm going to do is, I'm going to do something called unrolling in time. So what is unrolling in time? This is something you need to understand about recurrent neural networks, because when you understand what is unrolling in time in recurrent neural networks, actually you understand how they work. So before getting to this slide where I unroll it, look at this. So at a time instant, I'm feeding this X, okay? So I'm going to call it, let me get my pen. So at a time instant, I feed XTI. Let's say this is the vector, this is XTI. And there are some states. If it is the initial, it's the first time I'm feeding something, these are usually zeros. So I concatenate them and I obtain the next state. Then I feed another X, XTI plus 1. I feed it, these have changed, so they are not zero anymore. Concatenated, another state is created. I feed it, another state is created. I feed it, another state is created. So for example, if I have fed from XTI to XTI plus S, this is a S plus 1 sequence of X vectors, right? That's the idea. But when I feed new X, I'm feeding it on top of this representation. So what I'm going to do is, I'm going to unroll this representation in time. So instead of showing it as a feedback connection, think of it this way. I fed XT0. These were the initial states. Let's say they are all zeros, okay? So x takes 0 and zeros concatenated. This is the vector that is fed to this network. And I have the new A's here. So A1, so sorry. So after I feed this is the core RNN. We don't have the output here, the core RNN. I have A1 here. So A1 will be the next input. So instead of feeding it to myself, I'm creating a clone of this guy here. I'm feeding it to here. And I'm feeding the next sequence, X1. And I'm obtaining A2 here. When it goes to TS, actually, I have not S plus 1 length sequence fed to this guy. So as you can see, when I represent this network in this unrolled in time representation, it doesn't look like a recurrent neural network anymore. Because a recurrent neural network, I was feeding it to myself. Instead, since this is not S, guys, let me just correct it. This is not a typo. S plus 1. I'm feeding S plus 1 length sequence of vectors. I've cloned this. I have this network. I've cloned it. Exactly same supernode. Here and here and here and here. So I fed it, concatenated it. I've got the new inputs, hidden states. Hidden states. So it is like a deep neural network where each of these are layers of K nodes. But the only difference of this guy from a feed-forward neural network with S plus 1 layers is all layers have the same weights. So it's cloned layers. So when you represent an RNN like this, it's called the unrolled in time representation. And in that case, actually you're not feeding the new state to itself, but to its clone, and it doesn't look like a recurrent connection anymore. If you draw the computational graph of this guy, it is not recurrent. So unrolled in time representation is, in a way, putting the recurrent neural network architecture in a graphical computational graph representation where there is no recurrency. I mean, there is recurrency, but we are constructing the graph as if there is no recurrency because we clone these supernodes and we use the clones. Does this make sense, or are there any questions? Understanding the unrolled in time representation is very important, guys, because when you convert this to a feed-forward looking like computational graph, well, it is a computational graph now. You can apply backpropagation, you can apply training. It is like a normal network anymore. The only difference is they have the same weights. Okay, I mean, it will settle more in time if you have problems. And remember, we have added an output layer in the previous slides. Remember the output layer? I'm putting the output layer as clones here. So this became like a sequence to sequence problem, right? So I'm feeding a network, so I'm feeding an input, and there is a, in the recurrent notation, let me say, there is a output layer here. So output layer is a fully connected layer. It's providing me an output. I feed an X, I get an output. I feed the next X, I feed the next, I get the next output. So I represent it this way. So I'm feeding a sequence of vectors. I'm getting a sequence of vectors. So this is actually a sequence to sequence problem. Like machine translation, like language translation from English to German, kind of. Actually, this English to German machine translation architecture is not very different from this. It is different from this, but it is the case. And the network computational graph I've created is, I mean, looking like not feed forward, not recurrence. which will help me. Because if I could put something in a feed-forward computational graph representation, I can apply backpropagation to it to train it. I mean, that's the idea. The reason that I'm trying to visualize the recurrent node in a non-recurrent depiction is when I could think of it as a computational graph without recurrency, a directed acyclic graph, I can apply backpropagation. If I can apply backpropagation, I can train that network. Good. Makes sense now. So in this one, I have n-log features. Feature is the length of a single element of the sequence. So at each time step, the sequence has n length features. I've got an s-long sequence. It starts from T0 to Ts, so it is not s, it is s plus 1, but it is a typo in the slides. The input is m-long. Each input at each instant is m-long, the vector size. However, since this is a sequence-to-sequence problem, when I feed s plus 1 length sequence, I get an s plus 1 output sequence. But each input-output instant element is m-long because I have m nodes in the fully connected output layer, right? Remember this guy. So this was m nodes. Is m. And finally, I have k hidden nodes, which means in the supernode representation, I have k nodes. That's why the hidden states that evolve in the sequence dimension, let's say time, are of k dimensions. This is a mathematical picture of what a simple vanilla RNN with an output gate looks like when it's unrolled in time. Good. So the formula doesn't change. This was the formulation, and it is the same, guys. So this formulation is actually this guy. The only thing is, when you're training this computational graph, these weights will always be the same. They are the clones of each other. Okay, let's go over the formulation. We've already gone over it. I mean, maybe you should also go over it yourselves when you get home. That would be nice. So, I think at this point, we have a very solid understanding of what a recurrent neural network is and how we can represent it unrolled in time so that it looks like a computational graph that we can apply backpropagation to. Okay? So let's see how we can make different variants of this model. Because by creating different variants of this model, we will be able to apply this model to different type of problems. Like how? This was the basic RNN architecture with an output gate. It corresponded to a many-to-many model because we had many inputs and we had many outputs, like a sequence-to-sequence problem, right? But when we talked about the type of problems we could solve, we did not necessarily always talked about sequence-to-sequence problems. We talked about, for example, classification problem, which is many-to-one problem. When you feed a sequence and you make it single decision. This has been something close, kind of. So that is not a many-to-many problem. Can we make a many-to-one problem out of this architecture, and how? That's what we are going to explore now. Okay, so it gets an S, again, not S plus 1, sorry. Length sequence as inputs. Sequence feature dimension is n, but doesn't matter. And provides S plus 1 length sequence as output, many-to-many. Actually, the problems that we talked about, the classification, etc., they all correspond to different I/O types, input-output types, which are not necessarily always many-to-many. It could be one-to-one, one sequence to one sequence, output. So when it's one, it is not a sequence, you may say. We are going to talk about that. For one-to-many, you feed something and you get a sequence. You feed a single element and you get a sequence. This is still a sequence modeling problem because you are modeling the sequence at the output, not in the input, at the input. So still a sequence. We are going to give examples and talk about them, don't worry. One-to-one with delay. What is delay? We are going to talk about it. Many-to-one, you feed many things and get one. Classification example, you want to classify a sentiment classification, for example. That example we've seen in the previous hour. Somebody has written a comment. Is it a good comment or a bad comment? I mean, people write comments about a movie. How many stars did they, how many stars does that comment correspond to? That's a classification problem. You're classifying that comment to up to, I mean, it's more like a regression problem. You're putting a value between 1 and 5, whatever, 0 and 5. And many-to-many with delay. We are going to talk about what delay is. Let's see. One-to-one. I'm feeding an X. I'm getting a Y. Is this the first, because I'm feeding one sample, and I'm getting one sample. Well, it sounded like it is not a sequence problem, right? So why am I using recurrent connection then? Well, that's not necessarily true. For certain specific problems, this could be the case. Because different from FNN, each time you call this, you may need a dependency to the previous times you called it. We're going to think of an example. So if you want to correlate each time you call this function, even though it's one-to-one, input-output relation is one-to-one, it still needs to have some sort of memory state inside it to have it. So a nice example is, you see in the slides, if you have the slides in front of you, like drawing a card from a deck. When you draw a card from a deck, I mean, there are 52 cards in a deck, right? If I don't remember it wrong, you get a card. If this guy has no memory, it fits FNN, there's the possibility that you could draw the same card the second time you're running it, but you don't want it to happen. When you're drawing a card from a deck, you assume that the first card you've drawn is lacking in the deck, right? So it's one-to-one problem with a memory. So one sequence to one sequence. So that's what we are going to do. We are going to think about different I/O types in recurrent problems, sequence problems, and we'll try to find an example for that problem, so that this will give you a broader idea about what sequence models are. Because in your real-world problems, in your projects, at some point you will be able to say, "Oh, my problem is a many-to-many problem. That's why I need to have some sort of RNN inside it. Maybe I should use LSTM," you're going to say, after the next week, because LSTM we're going to learn next week. Whatever. So this was one-to-one. Other one is one-to-many. What is one-to-many? Well, remember the original unrolled in time representation. It was many inputs and many outputs. Just think about it for a time. I feed the same input to all sequences. It would be like feeding the same thing all the time. And you're getting the outputs, different outputs. So this would be actually, in practice, a one-to-many problem. Although you're feeding many things in the input, since it's the same thing, you're not providing any new information to the system. So that becomes a one-to-many problem. So you can simply mathematically model this network as a one-to-many problem by feeding the same input, always the same input. So this is like calling the vanilla RNN for multiple times using the same fixed sized input with same values and observing the outputs. Okay. So this is again S+1. You're getting these outputs. So what could be an example for it? Think about an example. I mean, it's written in the slides, but I'm giving you some time to think about it. I think music generation is. You're saying that, for example, the input is, you're calling the scale of the song, and it's creating a solo, I don't know, in that tone, in that scale. And there's studies. I mean, it's very simple. You can do this. There are many nice examples in GitHub. If you're into music and music composition or generation, try it. Maybe we'll try it in following weeks, because that would have made a nice project. You already have your project ideas, but don't worry. Okay, so this was a one-to-many example. Now another example is one-to-one with delay. What is delay? Guys, I'm feeding a sequence. I'm getting another sequence or a single result. Sometimes the network needs to evaluate for some time to make that decision. The sequence model needs to do this. We see this example a lot in control systems. If you're coming from engineering background, especially electrical engineering, control systems have some sort of delay, that natural delay that comes from their nature. So sequence models, some sequence models can be designed with delays, guys. Again, this is one-to-one, the input being one, meaning you're feeding the same input. While you're feeding the same input, just like the one-to-many problem, you are getting multiple outputs. But imagine we are ignoring some number of outputs, which will correspond to the delay we're going to have. We are reading only the last output, the third output. If you're reading only the third output, you are ignoring first two, which means you have a delay of 2. This is the concept of delay. So this is like a vanilla FNN called for the same input multiple times, but some of the outputs removed. Good. So we have practically a single input, practically a single output with delay. So what is ignoring, guys? Have you ever thought that? So what is ignoring? Who is ignoring that? Who the hell cares it's ignored or not? Ignoring will make sense when we are training the system. During training, we won't calculate the loss according to this. The loss only will be calculated from here. And since this is the computational graph, the loss, the gradient of the loss, will be back propagated from all these directions. If it was a one-to-many problem, the loss would have been calculated from all these boxes, and the gradient will flow from multiple directions, from multiple sources. So ignoring is all about the training parts. That's how you ignore it. And in practice, after you train it, you ignore that output. That's how it works. But the important part of ignoring is about how you train it. Never forget that when it's unrolled in time, these representations are simple computational graphs. And to a simple computational graph, you can apply backpropagation. While you're applying backpropagation, there should be at least one loss function. There could be multiple loss functions. And when you have a loss function, you are calculating the derivative of the loss function, or if it is multiple loss function, the accumulated, the summed derivative of the loss function with respect to some parameters that you want to update. I've just summarized deep neural learning training with 5 sentences. That's the idea. Okay, let's think about where there's a need for a delay or repeat. We'll talk about loss later. Like a second order control system, there's delay. I mean, if you're coming from engineering background, it will make a lot of sense. Okay, I mean, they are usually modeled as many-to-many with delay, but I mean, that could be a control system where you're trying to get a single value, for example, parameter estimation. I don't know. Let's not get into the very details of it. We are trying to understand recurrent models as computational graphs unrolled in time. So many-to-one, it's almost the same architecture with one-to-one, but the thing is, you are not feeding the same input. It is many, input many, output one, IO, input, output. You're feeding different inputs. Since it's one output, you are ignoring these. Ignoring this means you are not using the loss of these guys during training. Only the last one. So training them will be the same as well as one-to-one with delay problem. Because in one-to-one with delay, remember one-to-one with delay, we had an input, we were ignoring these. In many-to-one with delay, the input changed. That's the only difference. So the mechanism to train it, apart from the fact that the input changes, the mechanism to train it, the loss flow, is quite simple. Okay, example, many-to-one. For example, action recognition from a video, many different frames. You don't care what it says in between. You just want to look at the final result because you want that historical knowledge, the states, to accumulate to a point which is the perfect decision. So you ignore these outputs in training. Many-to-one is an action classification from video. Vision guys will know this and like it. And many-to-many with delay. I mean, depending on the number of output you ignore, many-to-one problem can be converted to many-to-many. Why would I need a many-to-many problem with delay? Well, actually, there's a very simple example. Think of this simultaneous translator who does translate an important guy's speech in, I don't know, Davos, for example. They wait for a moment. And the guy starts talking, the important person from African Republic somewhere. The guy waits and starts to speak because it needs some time to get some number of words to make up or guess the meaning of the incoming sentence and provide the meaning to you. And actually, that delay is a part of the nature of the problem. So you just ignore some of the outputs, but not all of the outputs. And in this case, in this computational graph, the gradient flow is from multiple sources, which is something quite trivial for backpropagation because in PyTorch we have this network where while you're creating the network, it's creating a graph. And for recurrent neural networks, it is this special structure. It can unroll it in time automatically. So when you have loss from multiple parts, it's accumulating them, nothing else. Okay, so a good example is language translation, machine translation, because you need that delay there. Okay, actually, this was what all I'm going to talk about. This is too much. I mean, we have done. We've tried to do a gentle introduction to the idea of recurrent neural networks. It was gentle, but it was heavy. So I recommend you go over these slides, and I strongly recommend you check these. I mean, there are very nice blogs that talk about introductory level recurrent neural networks. Because next week, we are going to talk about LSTMs, which is the fundamental recurrent architecture you can use in your projects, okay? And the big picture will make a bit more sense because what we've done this week was we've talked about sequence levels at a very higher level. Then we've jumped to the lowest level to the point where feed-forward neural network became a recurrent neural network with that feedback connection. Then next week we are going to fill the gap. The gap is the LSTM. It's an advanced architecture. It's like the CNN of recurrent neural networks, we could say. Okay, any questions? Any questions?